All right, I think it's time to start. Let me see this one, so the place. Okay, and what we're gonna do today is to talk about the quarter wave transformer. And then we're gonna do more examples, all right? So that is probably the only new thing that you're gonna see, very useful. And then we're gonna do examples of matching different loads to the A transmission line, all right? So we'll do more of this between now and tomorrow. Also, office hours today and I will send a note for that as normal. But then on the weekend, Saturday and Sunday, I'm gonna have review sessions. All right, 2 hours Saturday, 2 hours Sunday. Sunday is from 2 to 4. And I think Saturday is gonna be about the same. All right, same time. I'm gonna send a note. I think I decided to do it then because you're gonna be studying for that class as opposed to doing it early because you have all of these other finals. Is there any reason not to do it like that? Okay, so I will assume that that's how we're gonna do it. I will send you a note. Anybody has any questions about the timing for the finals on Monday?
Much from 3:30 to 5:30.
Yes. here. And the other class is in the morning, which was supposed to be, as they were supposed to have the original class in the morning and they changed it. Yeah. Yes. Yes, yes. Unless there is a reason for not, unless anybody is sick or something, and I have prearranged, I have come to an agreement with them ahead of time to take it from home. Unless you have that, and you have spoken with me and I have agreed, everybody's gonna be here. That's my expectation. Open everything as you normally do, but don't rely on that. Okay. All right, so quarter wavelength transformer is an important concept when we have, and a very quick concept for matching, when we have a real load. Remember we did a real load with a reactive matching? Okay, that is good if it's easy to do, but this is easier. So whenever you have a real load like I have here, for any value of the real load, then you can prove, and I will show how to do the proof, but I will just state how to do the matching here. You place in between your transmission line, which is the blue one, where this one says for now has 50 ohms. That's what I'm giving you, all right? And somewhere on the transmission line, you're gonna have a voltage source as we have done before. It's not necessary for me to put it here, but I will put it because this is a new concept for us and you may worry if I don't have it there. So this is vis-a-vis at some point along the line, but we know that this distance of the intermediate length of this intermediate section of line, it's a quarter of a wavelength. That's why it's called the quarter wave transformer. Okay. Now, this section of a line that has a new characteristic impedance C1 and has a length of a quarter of a wavelength can totally match the blue line here. So for example, can create, if, all right, let me also name the nodes, all right? So as you should do, A prime, B prime, C prime. See, I always name it. Okay, so that you can make the reflection coefficient at BB prime, this reflection coefficient, all right? Let me, in fact, move this a little bit. So make it smaller and move it here. It makes this reflection coefficient, which I call gamma at BB prime. And for us, the reflection coefficient is always, as we look from the source is behind us for this class, the source always behind us, towards the load. This gamma BB prime is 0, which means there is no reflection, all right? If the length of the line is a quarter of a wavelength and Z1 is nothing else but the characteristic impedance between Z0 and RL, the square root, I meant to say. The square root of the characteristic impedance of your input line and your load. That's why the load has to be real, all right? Characteristic impedance, you cannot take the square root. First of all, characteristic impedance is always real, always, okay? And in this case, to have a real characteristic impedance for the quarter wavelength section, which is Z1, you will need to have RL to be real. If RL is not real, that is not working, all right? Only therefore, remember that, because I can tell you how many students make that as a mistake. They put a quarter wave transformer when you have a complex load. Don't do that. Only for, of course, RL is real, but for ZL, real, to be accurate here. For ZL to be real, meaning a resistor or a real load, okay? Now, how we would prove that? Easy. I would find, to prove, therefore prove it, proof rather. Or prove the statement. All right, I will do the following. I will find, to find the reflection coefficient, okay? So gamma B prime. I would have, if I were to find that, I would have to know what the input impedance as we look towards the load at BB prime. Do you agree with that? So I will have to know this one here. So Z input at BB prime. Do you agree? If I know Z input at BB prime, then this one, the reflection coefficient, is going to be Z input at BB prime minus Z naught, because that's what I am on the blue line. It has a characteristic impedance of Z naught. And therefore, I will use Z naught for that, divided by Z input, BB prime, plus Z naught. So I have a question for you. Am I going to normalize this one? What was the condition for normalizing impedances for this class? We have a condition, so we don't make mistakes, that we only have one characteristic impedance. Here we have two, so do not normalize. Because if you are experienced, if you're an experienced user of the Smith chart, it's okay to normalize with whatever you want, all right? It's not true that Z naught is the only thing to normalize. But if you are not experienced and you normalize with something else, and then you don't take that into consideration when you work, you're gonna make a mistake 100%. So for every class I'm teaching, I'm asking people to normalize only if there is one characteristic impedance, okay? And that it only happens for us in the quarter wave transformer. That's why I'm not gonna normalize this. What I will do next is to use the formula for the impedance in the red line that has the load at the end to be able to find the input impedance at BB prime. So now, and I'm gonna write it there with red so you know. So where we know from our formulas that this one is now, what characteristic impedance am I gonna use for this? Since I'm in the red line, I'm gonna use Z1. See, so I'm gonna use here Z1. That's according to the equation, the expression we have. And then we have ZL plus JZ1 tangent. And this is I call it D, the quarter wavelength, beta D, over Z1 plus J ZL tangent beta D. Okay, we said that D is a quarter of a wavelength, where therefore D is lambda over 4. If D is lambda over 4, how much is beta D? Is 2 pi over lambda, beta is that, times D, which is 2 pi over lambda times lambda over 4, all right? And therefore, this goes and this goes, and I have a 2 here, this goes and this goes, and that is what? Pi over 2. How much is the tangent of pi over 2? That one, you're gonna have to have it in your fingertips. The tangent of pi over 2, how much is it? Who is gonna tell me? Yeah, it approaches infinity. Why? Tangent is sine over cosine. How much is the cosine pi over 2? 0 goes to 0. Therefore, tangent beta D is going to become so much larger than ZL that I have to assume that ZL for the numerator is so much smaller than Z1 tangent beta D that I can ignore it. All right. So, and therefore Z1 is going to be so much smaller than ZL tangent beta D that I can also ignore it. All right. So because of that, this equation here gives me that Z input of B prime is going to be Z1 here, and then we only have J Z1 tangent beta D divided by J ZL tangent beta D. All right. So this goes, and that gives Z1 squared over ZL. Okay. Now this is 2. Let us go to gamma B prime, which is the reflection coefficient. Under what conditions does this become 0? When does this become 0? When? When the numerator goes to 0. When does the numerator goes to 0? When does it go to 0? When Z input at B prime is what? Z naught. Therefore, if I go from that to 2, and I write here, I want to put everything on one page. So let me do this, move them a little higher up. Okay. Then from 2, now I can put Z input at B prime equal Z naught is equal to Z1 squared over ZL. And therefore, from here, what do I find? What I just told you in the beginning, that Z naught times ZL square root, if that becomes equal to the characteristic impedance of the quarter wave line, then we have a quarter wave transformer. That is we don't use the Smith chart for this. Why do we not use the Smith chart? Because what? Exactly. We don't use the Smith chart because we don't normalize. The Smith chart is only useful when we normalize everything. And in this class, we are forbidden from normalizing if there is only one, if there are more than one characteristic impedances in the problem. Okay, here there are 2, obviously, 2 different transmission lines. Now, another thing I want to show you. Do you see how I drew the 2 transmission lines? Why did I do that? To remind myself of the characteristic impedance visually, all right? Visual information for our brain. I mean, remember that, yes. I did not finish. D, I forgot the D. Thank you. Thanks. So visually is extremely important in these problems to get all of the information you can, all right? In engineering, we don't use anything that does not have information. You need to, so many times I say that, all right? Anything that does not provide you with viable information is useless. So whenever we draw something, there is a reason. Visual information, whenever possible, is the best way to get information than text. So that's why here what I do, and that helped me when I was learning about these things that I'm using, but now, when I have characteristic impedances that are different, I give the lines a different distance in between them. Physically means nothing. It's only symbolic. Why it is symbolic? And here I use colors. Let's assume we don't have colors, right? Why it is symbolic? Because it's very easy to make a mistake when you see lines just connected to assume that they have the same characteristic impedance. Over and over again, people make that mistake. So if lines have different characteristic impedances, even if it's meaningless that they are closer, all right, because they may or may not be, make them a different distance. So that reminds you at any point, no matter how tired you are, or complex or confused, that this is a different characteristic impedance. So that's why we do it like that. Okay, any questions about this? So if I ask in the final, if I give you a line and I give you a real load and I ask you to match it, to match the load to the line, the best way to do it is to use a quarter wavelength transmission line. If you have the space, yes.
Wouldn't the line have a quarter of the wavelength?
Because of tangent beta D. If tangent beta D was not very big, that formula would not apply. And then your Z input at BB prime would never become Z naught. So you need that condition for your Z input at BB prime to be real. Otherwise, it would have been complex and therefore would never match to Z naught. See, that's why. Or an integer multiplier, an add integer multiplier, but you don't want to have a line that is this long. You want to have the shortest line. So the shortest is 1/4 of a wavelength. The next one is going to be 3/4 of the wavelength. But why would I use space for no reason? Extra. Waste, rather, extra space. Okay, the other approach would have been, if let's assume you don't have the space for that, quarter of a wavelength, you are at low frequency. For example, let's assume that you're at 1 gigahertz, 30 centimeters for free space wavelength. 30 centimeters, even a quarter of that, which is 7.5. It's a lot of distance. Let's assume you don't have that. Then in that case, what you would do, you would rather use a reactive component that you just place it, and then use the Smith chart, but find the shortest possible distance and see whether that makes sense, all right? So in design, there is not one possible solution. Your optimal solution comes out of a lot of constraints. But if I don't give you any constraints and I give you a real load, and then I want you to match it to a characteristic impedance, you use this one. Yes?
What do you mean by that, by matching the load to the line?
Matching the load to the line, to the Z naught line, your load here, let's assume, okay, let's do an example, and then you can see. The example that I will use is to, first of all, add, where I am? Oh. Okay, that's kind of interesting. Okay. Okay, let's add here, add page. Okay, so let us do a particular example. Say, consider in the above, so example here, let's assume, what could I give you? I could give you the frequency, F equals, say, 5 gigahertz. And then I give you the load, ZL is equal to 150 ohms. And then I give you the input, the blue line, the input characteristic impedance to be Z naught is equal to 50 ohms. So what does it mean matching? When I say matching, match the load to your line, I mean make the reflection coefficient 0. Why is that? Why do I want to make the reflection coefficient 0 in this line? Remember what we said? Yes, so we don't have any power to go back to the source. We're gonna send everything to our load. Whatever leaves the source, we want it to go back all the way, the real. We don't care about the reactive. We don't care about the energies, like the capacitive reactive effects that are stored. This is not real power. Real power is what you generate from the source. 1 milliwatt, 3 milliwatts, 10 milliwatts, 50 milliwatts, very expensive power in high frequencies. We want all of this to go to our load, all right? It only happens if in the transmission line that connects to the source, on that line, your reflection coefficient you do things next to the load, so the reflection coefficient becomes 0. And that is called matching, all right? We match the input impedance at that point, or your load, if you like. You do things obviously in between, but you match eventually your load to your line. Okay, so in this case, number 1, how much is the wavelength? Yes, thank you. Tell me number. How are you gonna do that to remember? The wavelength at 10 gigahertz is 3 centimeters. Remember that. How much will be the wavelength at 5 gigahertz? 6 centimeters. Why is that? Because when the frequency increases, the wavelength decreases. Remember the two? Because the product is C. So always remember, if you do that, you're not going to have to go to your calculator and calculate stuff. Remember that at 10 gigahertz, the free space wavelength is 3 centimeters. And then from there, you easily find what is it, 130. What is it at 5? We said 3 pi is going to be 6 centimeters. What is it at 1? 5 times that, 30 centimeters. All right. When you go lower in frequency, your wavelength increases. When you go to AM, which are the radio stations, the AM, how much is the wavelength?
What's the station?
It's big for AM. How much is AM? Do you guys remember? It's kilohertz. Well, if kilohertz, let's take that, 10 to the third, megahertz, 10 to the 6, gigahertz, 10 to the 9. To go from gigahertz to kilohertz, you need 1 million. So from gigahertz to kilohertz, your wavelength increases by 1 million times. It's huge. And that's why people use it, because it goes around the earth, all right? Anyway, so remember that. Now, so here, in 5 gigahertz, the wavelength is going to be 6 centimeters. Because then, when I say match it, I mean, give me the geometry, give me the specifics, all right? So in this case, immediately, if somebody would tell me that and I see that my load is 150 ohms, I would say I'm going to use the quarter wavelength transformer. And if I use quarter wavelength transformer, then obviously I need to find how much is the quarter of a wavelength in physical length, since I gave you the frequency. So then I need to find 2 things. D, which is lambda over 4, I need to find it in centimeters. And then I need to find Z1. So now I know it's, since lambda is 6 centimeters, this is going to be 1.5. Well, no, sorry, what did I say? I don't know what I said. Since lambda is 6 centimeters, divided by 4 is going to be 1.5 centimeters, sorry, 1.5 centimeters. Okay, and Z1 is going to be the square root between 150 and 50. Which is, I don't know how much it is. This one, it's 50 times 150 square root. It's 86.6 ohms. So now you solve the problem. Because to proceed beyond that, you need to know what type of a transmission line you're going to have. And we have not spent that much time here in this class. So that's where you're going to stop. Because if you give me the characteristic impedance, and I know what kind of line I'm going to use, a microstrip with this kind of dielectric, with this kind of thickness, then I can go to the web, find a calculator, and find the dimensions of my line. Okay, so that is the result that I would like to see. Any other questions on this?
Yes. What we were trying to do here was matching the line.
We try to match the 50 ohm line. Look at this figure. We try to match the source to the load. We try to send all of the power from the source to the load. And because the source connects directly like that to the line, practically I'm going to make the reflection coefficient on the line, the blue one, 0. Yeah. Any other questions? Yes.
So for this problem, you have to use
No.
So, but if we're asked to use a Smith chart, find the values without a Smith chart, should we do it without a Smith chart?
Yes. If you can do it without the Smith chart, you do it.
If we're asked
Nobody's going to ask you to use the Smith chart if you have a real load. It's an unnecessary complication, you know? You use the Smith chart when you have to use it, when the Smith chart is simpler than math. But here you know it. You don't even have to do only a square root. You only in design, you use the tools that make it easier for you. Yes.
So no matter the configuration of the transmission line, as long as the load is real, we can use the quarterly transformer.
Yes, absolutely. When you say configuration, you mean the geometrical? Yes, absolutely. Mhm. Yeah. Yes. Any other questions on this? There are a lot of quarter wavelength transformers on circuits. As a matter of fact, people are using them preferably. It's from the, especially in microelectronics, high frequency, small wavelength. It's going to be a tiny thing. It's better than using an inductance, a capacitance. You see how you make capacitors like that? It's a big thing, you know. If you have real, why not use it? All right. Let's try now to do a problem where we have to use the Smith chart. And in this problem, I'll give you another example. So if that was quarter wave transformer, that let's call that example 1. So I'm doing that since it's going to be easier to make a copy and put it on. Okay, so example 1. All right, so let's put it here. Now we'll do a second example. Example 2, where we have to use the, let me also draw a line. Draw a line here. Okay, so example 2. This one we have done the solution, so I will ask your help. So I have the same here. I will take only the pieces that I like rather. So I will copy it so I don't spend time copy. And then I will modify, paste. Okay, so this one. All right, move this. This. Okay, and now I have this line that connects to the load. Oops. Anyway. Okay, so this one goes. All right, and then And this load now is reactive. This load, I will give it to you like that, is R plus J omega L. And here that has Z naught is still the same. Let me write it here. So what I give you is F to be 10 gigahertz. Okay, I give you that R is 80 ohms. And I give you that L, I have not computed that, but I would say, let's see how much it's gonna be. 2 pi 60, 10. Let's see whether 1 nanohenry will do it. But it's gonna be 10 to the 10th. Okay, that's gonna make it 60 something. All right, so 1 nanohenry. And now I want to match this one to my load, all right? Z naught is 50 ohms for this line. But I wanna match this with a shunt element. Shunt element means an element in parallel. So say match this using a shunt element. Okay, shunt means in parallel. Connected in parallel. What is in parallel connection? It's a component, all right? So in parallel means, as you will see, that it has to connect to the two lines. Not series as we did it last time, like this. So that's what the problem says. So now let me add one more page to give us some space. Okay. All right, let me think of how this is gonna look like. That's important, obviously. Here I have a complex load. I have not found it yet in all in ohms, so I have to do some work there. And then I have one transmission line, one characteristic impedance. Therefore, even if without me telling you, the easiest way is to use the Smith chart. But I have to redraw it a little bit so I can think of how this is gonna look. So I'm taking this one here, copy, I put it here, paste. All right, and then somewhere I have to break the line as I did last time. So I'm gonna go here in partial and say break the line here because I'm gonna add an element. Now, that does not change the full length of the line, all right? Maybe they also gave me the full length of the line. Let's assume that L, which is here, L is, how much is that? 5 centimeters. Okay, somebody gave me that. That is your constraint. From my source to my load, and the load can be a radiating element, you only have 5 centimeters. That's what they told me. No more than 5. So in this case, I'm going here. I cut it, but that does not change the length of my line. Why is that? While I'm cutting here, it does not change the length of the effective line. Because visually it looks like a big gap, but in reality, I'm gonna put a lumped element. So a lumped element, when you put it, is like at one point rather, all right? So to remember that, I put here a thin line like this, and then I will put my reactive element here. Now, I'm gonna indicate that as a Y. As Y, which is an admittance. Why do I put that as an admittance? Because eventually I know that we will have to sum them up in parallel, all right? So, excuse me, we have to combine them in parallel, which means, I said that ahead of time, we have to sum, it's easier to sum up things. And if you wanna sum things up in parallel, you have to work with admittances, okay? So, what is an admittance in a reactive? Here there are reactive elements. Remember? So I have to clarify some things for you. So you don't you write Y, but you write an impedance. So a Y is an admittance. If I have, which I don't know yet, but let's assume now something for you to remember. If my element is a capacitance, how much is gonna be if I call it Y sub S, all right? How much is gonna be the admittance for that? If it's a capacitance. We are in the phasor domain, all right? Don't. J omega C, exactly. Yeah, correct. J omega C. If it's an inductance, how much is your admittance? Exactly, 1 over J omega L, or minus J 1 over omega L. What does that tell you? That if your element is capacitive, then your Y sub S is gonna be positive. When your element is inductive, then Y sub S is gonna be negative. All right, so from the positive or negative we are gonna find on the Smith chart, you know what kind of element you're gonna put. Okay, let me now do the same thing for impedances. If I were to use an impedance somewhere, all right, so I'm gonna use the same thing. Let's assume that I have a series capacitance, because that's where we put impedances. Let's assume that I have a series capacitance here. Series, all right? How much is the impedance of that? If I call that, and I call this Z sub S, how much is the equivalent of this? Yes, it's gonna be 1 over J omega C, or minus J 1 over omega C. And if I have an inductance in series, that I call it Z sub S, how much is that? Exactly. So if you have impedances which are negative, then you know it's a capacitance. That's why on the Smith chart, when we go under, it says capacitive load. All right, when you use for impedance, is capacitive load is south. An inductive load is up for this reason. So you need to remember those things. Okay, so now I have to put, I told you that I want a parallel. All right, that's part of the problem. So let's try to solve it using the Smith chart. All right, what do I have to do before I use the Smith chart? I have to normalize everything in the characteristic impedance. Therefore, I need to find ZL. How am I gonna find ZL? ZL here is gonna be, what did I give? 80 plus J 2 pi. F is 10 to the 10th, all right? 10 gigahertz is 10 to the 10th. And then L, which is 1 nanohenry, which is 10 to minus 9. Okay, and that is ohms. And therefore, this is going to give me 20. Excuse me, let me write the 80 first. 80 plus J 20 pi. And all of this is going to be in ohms. And in fact, to find 20 pi, I'll go here, 20 times pi is about 80, 62.8, I will say 63 approximately. So this is going to give 80 plus J 63, and all of this is in ohms. Now I'm good to normalize, okay? So now ZL normalized is going to be 80 divided by 50, which is Z naught, and gives 1.6, plus J 63 divided by 50, which is 1.26. And I found the normalized load. Now I'm ready to go. What else though do I need to do? I need to do one more thing. I need to see to get a sense of my length, but in what? In wavelengths. So I have given that my length, L, is 5 centimeters, but my wavelength is 3 centimeters. So here, L is gonna be 5 divided by 3, which in fact, it makes it what, 1.66, I think. Anyways, say 1.7. Just to round up things, I don't like long numbers. So 1.7 lambda. Okay. Why do I need to look at that? Because I need to have a sense of my space on the Smith chart. How much of a length do I go around when I go on the Smith chart to cover the whole chart? From the beginning until the end, how much is it? Yes, half a wavelength. All right. So now I'm going to the Smith chart. Let me erase all of this. You remember those lines? I put them there so you guys remember. Remember the red ones are what? Resistive. Green ones are what? Reactive. Okay. And then there is one more circle we draw from the center. The center. These circles that I normally make them purple, look like this, sorry. Okay, here, and I will make them a little dense there. And there are multiple like this, yes.
So sorry, could you please repeat how you express the distance in terms of the wavelength?
Yes, I find the wavelength in physical units. The wavelength 3 centimeters.
Oh, because of the frequency.
Yes, yeah. And then I go and divide 5 centimeters by 3 centimeters. Okay, so you remember these 3 types? These are the 3 circles we use. Don't become creative with the Smith chart. There is no creativity there. Follow the line. Okay, so there I will erase them now all. Let me do it here. Okay, that's the only place where we don't do things, don't create things. All right, so now what is the first thing I'm gonna do? From the things that I found. What is the first thing that you're gonna do? Find it and then find it on the Smith chart. Okay, so 1.6. Okay, here is the circle. I will draw it now. I will not normally do it, but at this moment, let me see. Red, okay. It's let me erase these ones. So you have to be neat on this Smith chart, all right? It's gonna be 1.6, we said here, starts at this point. In the exam, I don't wanna see circles. If I see people trying to solve the Smith, okay, not like that. Okay, let me do one circle quickly. And then I'll move it. Okay, and this has to go from there. All right, see that? So you cannot do things by hand in circles here because the results will be so off, all right, that you cannot do that. All right, so please take a compass if you have no other way. Go and buy a small one from the bookstore, all right, so you can do it. There's no other way of doing it if it's on paper. Then, unless you are good enough, so you don't have to draw it, but you still, for the other circle from the center, you will have to do it. If you're good enough in seeing the circles, you don't have to draw them. Yes,
Will you give us one of these charts on the test?
yes, I'll make copies.
Thank
Sure. And then, in fact, somebody here had the better Smith chart. Was it in this class? Who was here who spoke with me and I liked your Smith chart? It's not today. So I'll figure it out. But there was a better one because it does not have all of the, anyways, depends. I'll give you this one. Okay. All right, so now then we find the reactive part of the impedance was 1.26. Where do we read 1.26? Out here. Out here, we read it. In fact, I know what I have to do, so I don't. So we read that out here, okay? So 1.2, 1.26. Go here. 1.2 is here. Okay, 1.3 is here. So 1.26 is going to be somewhere here. Okay, and therefore I'm writing this. All right, and where it intersects is my point. And usually what I do on my Smith charts when I work on them, so I don't forget, I go here and I write the impedance that I found. Okay, so I write here that this is ZL normalized, and it is 1.6 plus J 1.26. Okay, and I do it like that. Then I erase these two circles. Okay, now I have the impedance. What do I do next? Yes, the circle of which we call of the transmission line. In fact, that tells you how to move from this point. That circle has the center at the center of the Smith chart, goes around like this. Okay, but it has to have the center, it has to go around from the point, but it has to be bigger. All right, something like that. Okay, there. Okay. All right. Now, let me make that a little bigger, a little thicker. Okay, now I have to move from where? I have to move backwards from here. I have to move along this direction. I need to find this point here, all right? So in fact, if I name these points, which I should, this is at BB prime, and this point is C prime. I always go A for source, BB prime for the load, and whatever is in between, C prime. I need to, so this point here, it shows where I am at BB prime. This is point B. And the center of the Smith chart is going to be right after point C, or I would say it's going to be point A, all right? Because anywhere, if the reflection coefficient is right after, I mean, towards the source, if the reflection coefficient is 0 here, is 0 here, it's going to be 0 here too, all right? So I'm going to go to the center. So the point, I'm going to move on this line from point B to point C. And in fact, you know, here is what the best thing to do, I would suggest for you, because it's going to be easier for you to see it. Even if they are the same points, you can put a point C here and C prime, and put a point D here and D prime. It does not matter that they are reversed, even if they are the same points. I mean, from the voltage point of view, the potential point of view, there is no difference between these points, but we do them like that because you can see your wave on this, on your way on the Smith chart, all right? So I wanna go there by a distance D until I find point C, C prime. But what is this point? When I go there, I will only add, first of all, I am an impedance, and when I go to CC prime, and then I have an admittance in front of me, what do I want to be there? I want to be an admittance there, all right? So when I go from my impedance at the end to by a distance D, in parallel, I want to change to an admittance. Okay, I can change to an admittance from the get-go. I don't need to wait until I travel. So practically, if I change my impedance here to an admittance, then I can travel from there. I can see what I'm saying. I can change my impedance to an admittance from the beginning, not later. So to do that, I will write the diameter of this. And then I will find this point. This point is still B. I have not traveled on the Smith, on the line. It's just I changed, by doing that, I changed from an impedance to an admittance. So practically, I can go here and I say, oh, that's nothing else but my YL normalized, okay? Now I'm in an admittance space. Nothing else changes. So now I have to move on the line, which is the purple. I have to move until when? Until I find the place where the real part of this admittance normalized is 1. Do you understand why? The admittance now has to be 1? Because, let me write here to remind you. Z sub gamma, you remember that, isn't it? That, excuse me, you remember, I want to make, let me go back a little bit here to write it explicitly. In this problem, all right, what do I want to do? I want to make gamma at BB prime, I want to make it 0. But how much is gamma at BB prime? Is going to be whatever this load is here, or the inverse of that is an admittance. Whatever this is there, it has to be equal to Z0, because this one, gamma at BB prime, is nothing else but Z input at BB prime minus Z0 over Z input at BB prime plus Z0. If I were to change that into admittances, all right, how would it go? An admittance is the inverse of these impedances. The equivalent to that, it would have been Y0 minus Y at input at BB prime, Y0 plus Y input at BB prime. So in other words, when you want to make your input impedance equal to Z0, then its admittance is going to become equal to Y0, because both of them are the inverses, all right? So practically, I want to make my admittance here equal to Y0. Real, it means real, which means that I have the normalized one is going to become 1. The normalized admittance, all right, if I want to make it Y0, which means that if here, if YL, if I find at some point is normalized, or Y input at BB prime, Y input at BB prime becomes to Y0, that means that normalized Y input at BB prime is going to become 1. Is that true? Which means that it's going to become a real number. Therefore, I have to move around this purple circle until I find the real circle that corresponds to 1. What is the real circle that corresponds to 1? This one. So practically, I have to move towards always from here. I have to move towards the generator. So this always. Therefore, and I have to move here. You will see how I'm gonna do that. I will have to move from this point I move until I make the real part of this impedance normalized 1. Okay. I stop here. Why do I stop there? Because from there, I have, and I claim that this point here is nothing else but y input at CC prime. That's why you see, I claim that at this point, this is my y input at CC prime. So if I move on the line from BB prime to CC prime before adding anything in an admittance form, and I find that y input at CC prime, that real part of this has to be 1. So when I add a reactance, I can add a positive or negative in this case, then it's gonna go down the reactive part to 0 after I have added ys, and it's gonna give me eventually a 1. So what does that mean? Look at this little circuit here, okay? Look at this one. At that point, I can say, and I have taken a lot of your time, so I know, guys, you have to go. I will continue that tomorrow to finish it, all right? But what I would like you to do as an exercise, go through where I am right now and see whether you can finish it yourselves. And then I'm gonna continue it tomorrow because I don't want you to be ready to go. I want you to pay attention. Okay, yes. Not because you have to only sum up on the Smith chart. You cannot do inverse. See, if it's the impedance and it's in parallel, it's not gonna, you don't sum up two impedances in parallel. That's why you have to go to admittances.